Howdy! This is your friendly neighborhood physics teacher here, and we are going to review for your test that is on Friday. So on your review sheet, you see a couple of things just to give you a heads up about, I would know the meaning of vocabulary. You won't necessarily have questions like what is acceleration on your test, but knowing the meaning of the vocabulary will help you answer the word questions that are on your question, the word problems that are on your test. So knowing that, there is a Quizlet on Schoology. So there's a Quizlet on Schoology. Actually, on Schoology, there's a whole entire helpful link section. It's yellow. It has like 6 to 7 helpful links talking about different things. There's actually another review on there that's online that'll tell you the answers as you work. So if you go through this review and you're like, I need more work, I need more practice, there's an online review also. Also below that is an old orange folder, which hopefully that's where you found this video. But there's 6 other videos to help you out with this unit. So use your resources. Please use your resources. And Miss Verona and Miss Heath are also resources. So if you need help, you gotta ask. So know how to convert units. There will be maybe potentially a little bit of unit converting on the test. How to read a position time graph or velocity time graph. And so knowing how to look at graphs and what the slopes are, what the slopes of those graphs are, be able to determine if it's going in a positive or negative direction using context clues, and be able to use all formulas and the correct units that go with the variables, and also understanding frame of reference. So we're going to talk about all this stuff. So variables. So let's look at the variables. So if you see just a plain x, that is your distance. X, oops, as I put a delta. X is distance. And that is measured in meters. Delta x is your displacement. That's also measured in meters. If you see distance, if you're looking for distance or displacement, the question might be, how far? So it's asking for how far, it could be distance or displacement. If you have acceleration, you're looking for displacement. So your VI is your initial velocity. That is measured in meters per second. VF is final velocity, still measured in meters per second. Your delta V is just your change in velocity. Still measured in meters per second. If you're looking for your final or initial velocity, it'll ask for how fast. If it's looking for change of velocity, it'll be how fast did it change, so there will be change. How fast did it change? So the change would be in the question if you're looking for change of velocity. And last but not least, A is acceleration. And that is measured in meters per second squared. That squared is just to the seconds. It does not affect the magnitude or the number at all. That is just to the unit. And if you're looking for acceleration, it'll flat out ask you, what is acceleration? So you have your distance, displacement, initial velocity, final velocity, change of velocity, and acceleration. Looking at your equations, we will give you the equations on your test, so you do not have to memorize them. The only thing you need to know is this stuff up here, what the variables mean and what's the unit that goes with the variables. Because sometimes in the questions, it doesn't say your velocity is this. It might just give you a number with a unit. Knowing that unit will help you know what variable goes with that number. So our first question says, fill out the last column below, either speed up, slow down, or constant speed. So best thing to do is think about is your graph stacks. So think about at your velocity, talking about this, so this is the direction. So knowing if your velocity is positive or negative, you're dealing with the direction. If you remember, your acceleration is the slope of your velocity. So this is giving you your slope. So for the first one, 1, 2, 3, 4. So we're going to draw velocity time graphs. So for number 1, so this is your velocity, x-axis is your time. Remember, anything above the 0 line is positive, anything below is negative. And that's positive direction and negative direction. So anything above the positive, the 0 line is a positive direction, anything below is a negative direction. And your slope, so telling your acceleration being positive or negative, that's telling you your slope. So the first one, you're in the positive quadrant, positive slope. So positive slope means it's slanting up. So your numbers are increasing. Are you speeding up or slowing down? That would be speeding up. Because your numbers are increasing. So now, what about number 2? So number 2, positive direction, so we're in the positive quadrant, negative slope. Negative slope means you're slanting downwards. So our numbers are decreasing, so we'll be slowing down. Number 3, we're in the negative direction. So we're going the negative, positive slope. So positive slope means we're slanting up. But think about your numbers on this case. If this is 0, this goes 1, 2, 3, 4. Well, then the numbers 1, 2, 3, 4. And remember, in physics, negative just means direction. So our numbers are getting smaller. So this would be slowing down. So then for number 4, we're in the negative direction, negative slope. So our numbers are getting bigger. So we are now speeding up. Remember, for velocity time graph, your slope is acceleration. Your slope is acceleration. So next, we're going to draw the three graphs, and I've given you like a little example. And we're going to draw your three graphs. So you can kind of see how they interact. It's very similar to your graph stacks. We're just adding words to it. So a person walking north at a constant speed. So north is a positive direction. North is a positive direction. And another thing that should be getting bell whistles is constant speed. Constant speed means there's no acceleration. No acceleration. So positive means our numbers have to be increasing. So if we're going up the graph on a displacement time graph, that's a positive direction. So we need to go up the graph at a constant speed. Another thing to remember is that for a displacement time graph, your slope is velocity. Your slope is velocity. So positive direction, constant speed. So we want a constant slope. So going up the graph means we're positive. Straight line, straight as I can draw it, straight line means it's a constant speed because that's a constant slope, a non-changing slope. Constant means non-changing. So we can take this information. So positive direction, remember, anything above the zero line is positive, anything below the zero line is negative. So we're in the upper quadrant. Constant velocity. The word constant means does not change. So the way we can show on a graph that something does not change is a horizontal line. Because that means over time, it's staying at that number. We're not changing off that number. And if you said it before, we'll say it again. For a velocity time graph, your slope equals your acceleration. So looking at the slope of this graph, your slope is 0. So it's going to be on the 0 line. Which makes sense because constant speed needs no acceleration. So it means my acceleration is 0. So a person walking north at a constant speed, your position time graph will be a diagonal going up because constant speed, your slope is constant, going up because it's positive direction. Your velocity would be a horizontal straight line because it's not changing. That number for velocity is not changing. So over time, that number is not changing, and that slope of that graph is 0. So our acceleration is 0, which makes sense because constant speed means no acceleration. For the next one, you have a person standing still. A person standing still. So that is your displacement changing? No, because you're not moving. So again, to show something that's not moving, or to show that's not changing, you just do a horizontal straight line. What that's saying is over time, I have not moved off of my spot. And since velocity is your slope, that's a zero slope, your number is not changing. So therefore your velocity is 0. And if that's still a 0 slope because it's still horizontal, so your acceleration is 0, which makes sense, right? Because you're not moving. You're not moving. So a person walking south and then back home. So walking south and then back home. There's actually 2 graphs this could be because I was not specific. So the first one will keep it simple. So a person walking south and then back home. So walking south and then back home means they turned around. So they turned around. So walking in the negative direction, negative, it's negative if you're going down the slope, going down the graph. So if you're going down the graph, it's negative. If you're going up the graph, it's positive direction. So negative direction going down the graph, positive direction going up the graph. And now you look at your slopes. So you have a constant in the negative, and then you have a constant in the positive. And since it's constant, you have constant velocity, constant speed means you have 0 acceleration. Another way it could be, because it was not specific, is they could be accelerating. There's actually several things it could be doing. It could be slowing down, could be speeding up. So it could also be accelerating. So if we have a person speeding up in the negative direction, then a person speeding up in the positive, your graph would look something like that. And then you're going in the negative direction, so you're below the 0 line, speeding up. And then speeding up. So speeding up in the negative, and then you're speeding up in the positive. And then your acceleration would be broken too, because you would have a acceleration, negative slope, and then positive slope. And you could do this for each one. You could be slowing down. You could be speeding up, slowing down. It all could be changing. So you could have all different varieties in this. Your test will be a little bit more specific, but I just wanted you to see that technically, since it wasn't specific, you could have a different answer. For accelerating north. You have your displacement time graph again. You have a velocity time graph. Acceleration time graph. So person accelerating north. Accelerating north. If you see the word acceleration, you're going to see some type of curve in your displacement time graph. Some type of acceleration or some type of curve. So speeding up, remember speeding up is horizontal to vertical. So if you see a horizontal, so you can see how kind of that starts out flat, then it goes vertical, you're speeding up. North is a positive direction, so we're going up the graph. Up the graph, so that's a positive direction. So we're going to be in the positive quadrant, and that is a changing slope. Our velocity is changing, and it's increasing, so we're going to have an increase in velocity. And looking at that slope, that is a constant positive, so we're going to be in the positive quadrant, constant acceleration. If you want to see more examples, look at your graph stacks, but that's just giving you kind of a breakdown of some important graphs to consider. So how do you find velocity from a position time graph? We just talked about that. It is your slope. So if you're looking at a position time graph, your slope is velocity. If you're looking at a velocity time graph, your slope is acceleration. I'm harping on that. Maybe you should know that. So and then next thing is a graph. Just kind of, you can give a story to help you understand what's going on. But I'm just going to kind of break it down. So for your first little bit, so right there, for your first little bit, you are not moving because your velocity is 0. I'm going to go ahead and just highlight each little part, and then we'll talk about it. Okay. Makes it a little bit easier to break it down. So for your first part, your velocity is 0. Think about if your velocity is 0, what you're doing. You're not moving. You're not moving. So for the first few seconds, you're not moving. For the next little part, you're going below the 0 line. You can see your numbers are negative. So you're moving in a negative direction. So you're moving in a negative direction, but your numbers are increasing. So therefore, you are speeding up. You're just speeding up in the negative direction. So your next part, for your next little bit, you're still moving in the negative direction, but your numbers are getting smaller. So your numbers are decreasing. So you're slowing down until you reach the 0 spot. Until you reach the 0 spot. So then right here, that little spot right there, once you cross the line, so I'm going to circle that a different color. So when you cross the 0 line, the x-axis, that means you have turned around. Turn around. Now, remember, we're on a velocity time graph, so turning around just means you've crossed the 0 or your x-axis. Now, remember, for a position time graph, to turn around, you just change direction. So this one person turning around, one goes up, one goes down. But for a velocity time graph, to change directions, you have to cross the 0 line. So then, once you've crossed the 0 line, you're moving in the positive direction. And your numbers are increasing. So you're speeding up. Which kind of makes sense, right? Because if you're going in the negative direction, but you're slowing down, to slow down, so thinking about your car, for you to physically change direction or to turn, you have to slow down to be safe. So you would slow down, change direction, and then you could speed up and go about your way. So the next part of your graph, you have a straight horizontal line. Now this is a velocity time graph. So that means your velocity is constant. So you're above the 0, so you're in a positive direction. But your numbers aren't changing. So that means you have a constant velocity. You're still moving because it's a velocity time graph. You're still moving. Your velocity is just constant. It's not changing. For your next part, your numbers start going. So you're still in the positive direction. Your numbers are decreasing. So that means you're slowing down. Remember, when you cross the x-axis, you turn around. Just a repeat. And then right there, so you cross the x-axis, it's a repeat. And so that means once you cross the x-axis, you're in the negative direction. Your numbers are increasing. So you're speeding up again. You're still in the negative direction because you're below the x-axis, below the 0 line. Your numbers are decreasing. So you're slowing down. You're at constant, still in the negative direction, but your numbers are not changing. So you're at constant velocity. Then last but not least, negative direction, because you're still below zero line. Your numbers are getting smaller, so they're decreasing. And so therefore, you are slowing down. So hopefully that kind of helps break down a velocity time graph, seeing how which direction you're moving. So remember, knowing the direction helps you know if you're going up or down the position time graph, and knowing if you're speeding up or slowing down kind of knows, helps you with your acceleration, if it's a positive or negative slope. Okie dokie. So Ben Russian is waiting at a stoplight. When the light turns green, Ben accelerates from rest at a rate of 6 meters per second squared for a time of 4.10 seconds. So first thing we need to do is write down our givens. So our givens says accelerates from rest. Rest is a given. Actually have to read. You can't just skim and look for numbers. Rest is a given. Rest is telling you that your initial velocity is 0. And a rate of 6 meters per second squared. So rate isn't it's not velocity, it's not acceleration. So how you know what that number is you look at the units. So what unit goes with meters per second squared? Acceleration. So 6 meters per second squared. So I knew that was acceleration because of the meters per second squared. It did not tell me it was acceleration. I just knew that because I know my units. And then it gives me time is 4.10 seconds. Our unknown. We're looking for our unknown, what it says. It says, what is his displacement? So we're looking for his displacement. So we need to know what formula to use. So let's list out our formulas that we could use. We can use delta x equals vi times t plus 1/2 a t squared. We can use delta x equals 1/2 vi plus vf times t. We can use vf equals vi plus at. Vf squared equals vi squared plus 2a delta x. So the first thing is our unknown has to be in our givens. Our unknown has to be in our givens. So if there's an equation that does not have, if our unknown is not in our equation, we can't use it. So this one right here does not have delta x, so we cannot use it. Now let's look at our givens. So we need delta x. Do we have initial velocity? Yes, we do. Do we have acceleration? Yes, we do. We have time? Yes, we do. So we could use the first one. Let's keep going. So we need delta x. We have initial. We don't have final velocity, so we can't use that one. We don't have final velocity, so we can't use that one. So the only one we can use is the first one. So our delta x equals vit plus 1/2 a t squared. So now we substitute. So we're looking for our delta x. Our vi is 0. Our time is 4.10. 1/2 a our t. Oh, we have acceleration. Our acceleration is 6, and our time is 4.10 squared. So now we solve. So delta x equals, so you want to do your PEMDAS. So think PEMDAS at this point in time. So we need to figure out what 4.10 squared is. So we need to plug that into our calculator. Plug that into a calculator, you get 16.81. We have 1/2 6. Now there's no squared in this little section, so we can go ahead and just multiply that. But 0 times anything is just 0. 0 times anything is just 0. So that kind of situation kind of goes away. So now we have delta x. Instead of confusing people, I'm just gonna there we go. So now our delta x equals, and you can just multiply that out. You can plug that in your calculator and just multiply it out. You put 1/2 times 6 times 16.81. And you would get 50.43 meters. And that is your answer. Now, going back to this 1/2 times 6 times 16.81, I've had a couple of students that are trying to take that 1/2 and distribute. You do not need to, or should you do that? And it's because it's just straight multiplication. Again, think about your PEMDAS. So if you needed to distribute, there would be parentheses with adding or subtracting inside. So you first look at your parentheses. So parentheses only have one number in them. Okay, good. I don't have to do anything. Then you look for your exponent. Oh, I have an exponent. Need to take care of that. Then you do multiplication or division. So you do anything that's separated by a plus sign. So your 0 times 4.10 was separated by a plus sign. Your 1/2 times 6 times 16.81 was separated by a plus sign. So you just multiply those. Then you add or subtract. So once you get to the substitution part, it's algebra. You just plug it in. And since it's displacement, your units are meters. No naked numbers running around. Next thing is asking for our final velocity. Let's write down our givens again. So our givens. From rest, we know our initial velocity is 0. It tells us our acceleration is 6 meters per second squared. And our time is 4.10 seconds. We technically have another given. We know our displacement is 50.43 meters. If you do not want, if you're unsure if you got that question right, the one above it right, see if you can figure it out without using it. So if you don't want to use this one, if you're like, I don't want to know if I got that right or not, so maybe you don't have to use it. So let's figure out what our unknown. So our unknown would be our final velocity. Now we need our equation. So we're going to go back to our equations. So final velocity has to be in our equation. So we're looking, nope, this one, whoops, did not mean to erase that. This one does not have final velocity in it. Does not have final velocity in it. The other ones do. But do we have, now we do have displacement. Let's see if we can use it without using it. So we could do this one or this one. It is possible. But I'm choosing to do this one because it does not have displacement in it. And just in case I might have messed up the first time, I'm letting you know I didn't. I promise you that's the answer. But I'm trying to talk it through like how you might during a test. So let's use our final velocity equals initial velocity plus AT. Now we're just going to substitute. So we're looking for our final velocity. Our initial velocity is 0. our acceleration is 6, and our time is 4.1. Now, it's just math. It's just algebra. So 0 is still 0. 6 times 4.1, that gives you 24.6 meters per second. There we go. So number 6 says, if I move your desk 10 meters north and then change my mind and move it 20 meters south, what is the distance? And then, of course, what is the displacement? I'm a very visual person. You all know that by now, so I'm going to draw it out. So we're going to go, so if I put your desk here, your desk is now a circle. We're going to go 10 meters north. And then we're going to go 20 meters south. So what is the total distance? Remember distance? You just add it up. So you went 10, and then you went 20. Direction does not matter. Direction does not matter. So the total distance I traveled with your desk is 30 meters. Displacement. Direction does matter with displacement because it's a vector. Distance is a scalar. So now dealing with our displacement, our displacement equation is our final position minus our initial position. So our initial position would just be 0 because that's where your desk started. Final position would have to be, so if it's 10 up, this would be -10. How I got -10? Well, think about it. You went 10 up and then 20 down. So your first you did, so basically you would do 10 minus 20, and you got a -10. So your final position is -10. So your final position is -10. Your initial position was 0. So your answer is -10 meters. That negative just means direction. So I ended up putting your desk 10 meters south from the original position. So all that means. Number 7. If you kick an empty can that was sitting on the floor at rest and it moves 650 centimeters in 3 seconds, what is its acceleration? So let's write out our givens. So again, rest comes into play. Rest means your initial velocity is 0. It says it moves 650 centimeters. Do we like centimeters? No. So we need to convert centimeters to meters. So centi is a -2 exponent. Meters is 0. So that gives you a -2. That means I move my decimal 2 spots to the left because negative means you're making it smaller. So my displacement equals 6.5 meters. And my time is 3 seconds. Our unknown is acceleration. So that's exactly what it's asking for. It's asking for your acceleration. Our equation, let's figure out what equation to use. So looking at our equations, there they are. looking at our equations, we are looking for acceleration. So it has to have acceleration in it. So we cannot use that equation because it does not have acceleration in it. Our givens, we are given initial velocity, distance, and time. So initial velocity, distance, and time, and it has acceleration. We were not given final velocity, so we can't use these two because it has final velocity. We have to use the first equation. Where'd it go? There we go. So we're going to use delta x equals vi times t plus 1/2 at squared. Now we're just substituting. So our delta x is 6.50 equals our initial velocity is 0. Our time is 3 plus 1/2. We're looking for acceleration. Time is 3. Remember our PEMDAS. So look at it. Parentheses. Parentheses all just have one number. We're good. We have an exponent though. So 3 squared is 9. And then we can look at 0 times 3 just gives you 0, because 0 times anything, even if it's a variable, still is 0. Then we can go ahead multiplying. It doesn't matter what order you multiply in, so we can go ahead and multiply the 1/2 times the 9, and that will get you 4.5 acceleration. We need acceleration by itself, so we have to divide. So our acceleration ends up being 1.44 meters per second squared. So you will need to pick up your little brother from school. You start heading to school at 25 meters per second, and you realize you're going to be late because you were talking with your friends after school. So you are to accelerate at 2.5 meters per second squared for 20 seconds. How fast are you moving now? So let's write down our givens. So our initial velocity is 25 meters per second. Your acceleration is 2.5 meters per second squared. Your time is 20 seconds. Your unknown, you're looking for how fast are you traveling now. So you're looking for your final velocity. Equation. So let's go to our equations. So we're looking for final velocity, so final velocity has to be in our equation. Oh, look, I circled it. So final velocity has to be in our equation. That equation does not have final velocity in it. But we're given, our givens are initial acceleration and time. So we do not have displacement at all. We do not have displacement. So we can't use, because we don't have displacement. So we can't use that one, and we can't use that one. So we have to use the third one. So our equation is VF equals VI plus AT. Now we just substitute. We're looking for VF. Our VI is 25 plus acceleration, which is 2.5 times 20. Do PEMDAS, so you multiply first. So you do 2.5 times 20, which gives you 50. And then you add, and that gives you 75 meters per second. For 19, says if you drive your car 12 miles total during a 24-hour period and you park in the same spot each night, why is your average velocity during the day 0? Now, remember, velocity is a exponent. No, not an exponent. Your velocity is a vector. Vector means direction. So if you park your car, no matter what you do, but if you park your car in the exact same spot every day, even if you go do something different the next day, your displacement is going to be 0 because you're starting and stopping in the exact same spot. So therefore, since your equation is displacement over time, your velocity will be 0 also. Now, this next one says, think about your acceleration ramp lab. How did you find your velocity? So go back to your data. So you had your displacement, you had your time. So to find velocity, you just had to do your displacement over time using your data, and you were able to get your velocity. Another way you're able to get your velocity is looking at your slope. So y mx plus b, remember that m means slope. So if you're looking at your displacement versus time graph, you would also use that. But if you have your data, you can just use your displacement over time. So a boat is moving at a rate of 11.2 meters per second and sees an alligator. The boat is now going at a rate of 22.4 meters per second. With an acceleration of 4.3 meters per second, how far is the boat from the alligator? So let's write down our givens. So we have our first, so boat is moving at a rate, so that's going to be our initial velocity because that's what was first given to us. Boat sees an alligator, so now it's moving at 22.4 meters per second. So that becomes our final velocity. Flat out says it accelerates at 4.3 meters per second, or meters per second squared. So our unknown, we are looking for how far, which is our displacement. So our equation has to have displacement in it. Our equation has to have displacement in it. So this equation right here does not have displacement in it. We have final velocity, so we can't use that one. We have initial velocity, and we have acceleration. So looks like we're using that one. We couldn't use the first one because it didn't have final velocity. Couldn't use the second one because it didn't have acceleration. So we're going to use the fourth one. So VF squared equals VI squared plus 2A delta X. Now we're just going to substitute. So our final velocity was 22.4 squared. Our initial velocity was 11.2 squared plus 2. Our acceleration was 4.3. And we're looking for our delta X. Remember our PEMDAS. So we have to square first. So you do 22.4 squared, gives you 501.76. 11 squared gives you 125.44. And then you could go ahead and multiply your 2 times your 4.3, and you get an 8.6 delta X. You cannot add these two together. As much as people try to do it, you cannot add those two together. Do not add. The reason you can't add is because of this puppy right here. You can only add like terms. You can only add like terms. Since they're not like terms, not both of them have a delta x, you can't add. So we have to get the 125 on the other side. It's a positive, so the opposite of positive is a negative. And when you do to one side, you gotta do to the other. So once you do that over, you get 376.32 equals your 8.6 delta x. You divide, because it's the opposite of multiply, and you get that your delta x equals 43.76 meters. So you're playing around the elevator. You start on the first floor, go to the 5th floor. Then you go to the 3rd floor when you're caught by Miss Heath. Your punishment for playing on the elevator is to find the distance and displacement of your ride. Miss Heath tells you there are 4 meters between each floor. So again, I'm a very visual person, so I'm going to draw it out. So you start on the 1st floor. You go up to the 2nd floor, 3rd floor, 4th floor, 5th floor. So you travel from 1st to 5th, and then you travel from 5th to 3rd. Each little section is 4 meters. Each little section is 4 meters. So as you go up, how many did you cross? So I went up 1, 2, 3, 4. You went up 4. So 4 times 4 gives you 16. So you went up a total of 16 meters. You went up a total of 16 meters. So now you're going down. How many floors did you go down? 1, 2. So you're going to do 2 times 4. So you went down a total of 8 meters. So you're having to look for your distance and displacement. Your distance, remember, you just add up. So you would just add up the 16 plus the 8, and that'll get you hold on. Yeah, that'll get you 24 meters. But for your displacement, there we go. For your displacement, is your final position minus your initial position. So your initial position was just 0 because you haven't really moved any. So your initial position is 0. Your final position would end up being 8. Now, the reason your final position will end up being 8, because think about it, you went up 1, 2 floors. 1, 2 floors. So, because you're on the 3rd floor. So your final position will end up being 8. Another way you can think about it is you did 16 up, 8 down, so you just subtract and you get 8. That's your final position. So you do your final minus your initial. So your displacement is 8 meters. Think about when you drop something, what is the acceleration of that object? Does it change from object to object? Your acceleration due to gravity is always negative 9.8 meters per second squared. No matter what object, no matter which direction, if it's being thrown up or thrown down, your acceleration is still negative 9.8 meters per second squared. So frame of reference. So a couple of things that will help you here is if you're thinking about if your vectors are going in the same direction or your vectors are going in a different direction, and is if your observer is not moving versus if your observer is moving. So if your vectors are in the same direction, so they're pointing in the same direction, and your observer is not moving, you add the vectors. If your vectors are in the same in different directions, and your observer is not moving, you subtract. But if your observer is moving, that information ends up being flipped. You would end up subtracting your vectors and adding your vectors. So this was your homework on your frame of reference, and I want to kind of go over just a few little things. Hopefully it will help you understand it a little bit better. So your person. So we're going to do person and the boat. So we're going to focus on the person and the boat. So your person is not moving. So from the observation of the person, we're trying to figure out how fast the boat is going. Okay? How fast the boat is going. So the person's not moving. We only have one vector. So the boat is going 12 meters per second, and the distance and the direction still stays the same, west. Let's say the observer is the boat, and what it's asking for, how fast is the person. So again, the person's not moving, but the boat is. So the person still seems like they're going at 12 meters per second, so that's how fast the boat is. But since the boat is traveling west, it seems like the object is moving east. So when the object is passing a non-moving object, when a moving object passing a non-moving object, your direction flips. Your direction flips. And think about when you're driving the car and you're looking out. It looks like the trees are going behind you. I know you're moving, but it looks like the trees are going behind you. So your direction flips. Now, let's look at we're going to look at river, person, and boat. We're going to look at river, person, and boat. So the observer is going to be person. And we're going to take how fast the boat is. And we're going to take the river into consideration. We're going to take the river into consideration. So the vector, our observer is not moving because our person's not moving. Our boat is going 12 west, but our river is going 5 east. So going in different directions, but our observer is not moving. So we're going to end up subtracting. So you'll do 12 minus 5. And that would give you how fast boat is traveling. It'll still be traveling west, but the river is slowing it down a little bit. So that's for an observer not moving with vectors going in different directions. Now, if the boat was going with the river, it would end up adding. Now let's look at the river and the airplane. And we're going to make the observer the plane. So the observer is the plane. And we're going, how fast is the river going? So our observer is moving, going in the same direction, so we're going to end up subtracting. So the river will look like it's going at 120 meters per second. But since it's going slower than the plane, since the river is going slower than the plane, it'll actually look like it's moving west because the plane is able to pull away from the river. Another way to think about this is when you're driving on a highway. So if you're going faster than someone and you're pulling away from them, it looks like they're going in the opposite direction. If we flip it and our observer becomes the river, and we're trying to see how fast the plane is, we still subtract, but the plane does seem like it's going east because it's quicker than the river. So now let's look at the, we're going to look at the bird and the car. So we'll look at the bird and the car. So the observer is going to be the car. We're going to see how fast the bird is going. So we're going in the same direction. So you'll end up adding. So you just do 32 plus 17. And that gets you 48 meters per second. Now, from the car's observation, the bird is still moving west because it's coming at the car. And if you're going to flip that, and make the observer the bird, and we're seeing how fast the car is, it's still moving at 48 meters per second. And since the car is moving east, coming at the bird, it's still east. So the only time that the direction flips is when you're dealing with the observer not moving, and then the observer's moving, and you have your object not moving. Or when you have your object that's moving, it's moving in the same direction, it's moving faster because it's pulling away, your direction flips. So hopefully that kind of helps you with frame of reference. I only looked at a few things. But yeah, there you go. That's frame of reference. So 16. Miss Verona's brother was going on a fishing trip. His journey starts at mile marker 75 miles, or 75, and he travels for 225 miles in 2 hours before he realizes he did not update his fishing license. He had to return to mile marker 25 where the Walmart it was, and it took him 4 hours to do that. And we're going to find total distance, total displacement, speed, and velocity. I'll give myself a little bit more room here. Okay. So let's draw it out. So he's starting at mile marker 75. It's not telling you that he's going 75 miles. It's just giving you a mile marker. So that's his starting point. So that becomes his initial position. Then it states that he travels 225 miles, and he does that in 2 hours. So after that, he turns around and he goes to mile marker 25. He goes to mile marker 25. And he does that in 4 hours. So that's where he's stopping. So this becomes your final position. So let's find total distance. So it said that we went 275 miles. So let's figure out what mile marker he's at. So you would just do 225 plus 75. So you find out that he's at mile marker 300. And how I got that was I just took, he started at 75, he went 225, so that